Okay, so to wrap up section 4.9, we're going to talk about something called orthogonal complements. And this is a topic that we discuss in more generality in chapter 6. So there's a proof, or sorry, there's a theorem that we're going to talk about down here. But we're not going to prove it because we're going to encounter this theorem again in more generality in chapter 6 and prove the more general case there. Instead, let's just introduce what an orthogonal complement is. So for this for this definition, we're going to be working strictly in the vector space Rn for any n here. We say that a subspace of Rn, which we call W here, we're going to single out a subspace called W. And if we look at the set of all vectors in Rn that are orthogonal to all of the vectors in W, we call that set the orthogonal complement of W. And we denote it with this symbol right here, W. This is like a perpendicular symbol. So to illustrate an example, first we're gonna look at this case here. Show that the orthogonal complement of the plane 2x minus y plus 5z equals 0 is the span of the vector 2, negative 1, 5. And I'm not going to be super formal in how I show this, but we are going to think back to chapter 3 where we talk about the point normal equation for a plane. So imagine that I have this plane and I've graphed it in 3 space, in R3. Okay, we know from back in chapter 3, and if you've had calculus 3, you should be very familiar with this, the coefficients on my x, y, and z here go together into a vector that gives me the normal vector for that plane. So this would be a normal vector, 2, negative 1, 5. Notice that these are the coefficients 2, negative 1, 5 of the x, y, and the z here. Any vector that lies in this plane is going to be orthogonal to that, right? All the vectors in that plane would be orthogonal to this vector. That's what the definition of a normal vector is. So we know that at the very least, 2, negative 1, 5 is orthogonal to all of the vectors in this plane. This plane is like what I'm calling W, my subspace of Rn. Now, I wanted to show that the span of this of the set containing this vector is the orthogonal complement. So what that means is that we look at the set of all linear combinations of this, and any vector that's a linear combination of the vector in this set would then be also orthogonal to everything in the plane. However, if you have a set containing only one vector, then the span of that set is just the set of all scalar multiples of this. There's no additional vectors for me to add to the scalar multiple here. So if I look at any scalar multiple of this vector, remember that just gives me vectors that have the same direction as 2, negative 1, 5, but are stretched or flipped vertically, the other direction. All of those vectors create what's called a normal line for this plane. It's the line that passes through the plane at a right angle, and it's pretty easy to see that all of the vectors that are orthogonal to this plane would be on that normal line. Really any normal line, depending on where I wanted to put this point in the plane, but the vectors would still be considered the same vectors. So that's sort of an informal discussion as to why the span of this set would be the orthogonal complement. So in this case, the orthogonal complement it looks like a line, whereas the original subspace looked like a plane. Okay. Okay, so let's go down to this. So this is an important theorem that describes the relationship between W and the orthogonal complement of W. So if W is a subspace of Rn, then its orthogonal complement will also be a subspace of Rn. Again, if I'm thinking of this in terms of subspaces, this plane has to pass through the origin, which we know it does. This line containing all these vectors would also pass through the origin. Both of those are subspaces of R3. So the orthogonal complement of any subspace of Rn will also be its own subspace. In addition to that, the only vector that these two subspaces will have in common is the 0 vector. And again, in my example up here, you notice that all of these vectors point in different directions from the vectors in the plane. So none of the vectors that I've drawn are equal to any of the vectors in the plane except for this single point, which we think of as the 0 vector. Okay, and then in addition to that, the orthogonal complement of the orthogonal complement is the original subspace. So again, if I wanted to take a look at this line passing through the origin and find its orthogonal complement, well, its orthogonal complement would be the subspace W, the plane, because all of the vectors in that plane make up the entire set of vectors that are normal or orthogonal to all of the vectors on this line. Okay, and again, like I said, we're going to prove a general version of this in chapter 6, so we're not going to consider a proof here. Okay, here's a theorem that we will prove. And it also uses something that we talked about in chapter 3. So it says if A is an m by n matrix, then the null space of A and the row space of A are orthogonal complements in Rn. That's why we're talking about this here. In addition, the null space of A transpose and the column space of A are orthogonal complements. So notice all four of our fundamental matrix spaces are making an appearance here, and certain pairs of those are orthogonal complements of each other. So to prove this, we're really just going to prove A, and B is sort of a natural consequence of A. So A, the null space of A is the set of all solutions to the homogeneous linear system AX equals 0, right here. We saw in chapter 3 that any solution to that homogeneous linear system would be orthogonal to each row of A. I believe it was towards the end of 3.4 that we proved that. So we already know that if V is a vector in the null space of A, that makes it a solution to the homogeneous linear system, then it's automatically going to be orthogonal to all of the rows of A. But what's left to show is that V would be orthogonal to all of the vectors in the row space of A. Remember, the row space has more vectors in it than just the row vectors of A. It has all of the linear combinations of those row vectors. So what we do here is I'm going to denote the rows of A by R1, R2 through Rm. It's an m by n matrix, so there's m of them. Because W is a vector that we've selected from the row space of A, it can be written as a linear combination of those rows by the definition of what a row space is. So I express W as that linear combination. Here's the scalars in that linear combination. What I want to show is that V is orthogonal to W because I've selected arbitrary vectors in the null space and the row space. If I can show that they're orthogonal, then that would imply that any vector in the null space would be orthogonal to any vector in the row space of A. And remember, to show that two vectors are orthogonal to each other, you want to show that their dot product is equal to 0. So down here, I'm going to do just that. I set up v dot w, and then I take w and express it as that linear combination of those row vectors. Here, I can use some properties of the dot product, namely the distributive property to distribute v to each of these terms, and then the homogeneity property to bring the constant out of that dot product. So notice this becomes this down here. Now each of these dot products are a dot product of a vector from my null space with one of the rows of my original matrix A. And like we just said, those are all going to be orthogonal, V with any of the rows of A. So each of these dot products should become a 0, which is why I have K1 times 0, K2 times 0, and so on. All of these are going to be the scalar 0, and that adds up to just 0. So that establishes that V dot W is 0, or in other words, V is orthogonal to W, and that proves what we wanted to prove. Okay, so that's an interesting and useful fact. It gives some geometric intuition behind these spaces. The last thing I want to do in this section is discuss our equivalence theorem, because we're going to add a ton of equivalences to this. I believe the last time we talked about the equivalence theorem, again, remember the equivalence theorem uses a square matrix A. So we're specifically assuming A is an n by n matrix in this equivalence theorem. I believe last time we talked about it, we only got up to G. That was in chapter 2 where we talked about determinants. We're going to add all of these to our equivalence theorem. And I'm not going to go through the proof that the book does to show that they're all equivalent to each other. I'm basically going to talk through a rationalization for why these are all appearing here. So remember, this theorem says that if any one of these statements is true, then all of the rest are true. It does not say that this is true for any square matrix A. But basically, if A is an invertible matrix, then the rest of these properties are all automatic. So what I want to do is find a way to connect these new statements to at least one of these statements up here. That's going to help. That's going to basically give me the equivalence that I want. And again, I'm doing this in a very informal way. If you want to see a formal, more formal proof, look at how the book handles it. So I'm going to use B here. Notice AX equals 0 has only the trivial solution. So if this is true, I'm going to say that implies that all the rest of these will be true. Now, if that's true, remember this is the homogeneous linear system, AX equals 0, and we get the null space from this system. I'm not even looking at it. Sorry, I'm pointing up here. So if the set of solutions to this equation is only the trivial solution, only the 0 vector, then that implies that the null space contains only the 0 vector. But if that's true, then the null space has dimension 0. Remember, we defined the dimension of the 0 subspace of any vector space to be 0. That's the same thing as saying that A has nullity 0. So this statement here is a direct consequence of that. But that actually directly leads to this as well. A has rank n. So that's true because of the dimension theorem. Remember, the rank and the nullity have to add up to the number of columns in a matrix, but we have n columns in this matrix. So the rank is automatically going to be n from there. Now think about what that implies. If the rank is n, and it's an n by n matrix, we have n rows in this matrix. Well, that means the dimension of our row space is n. And that means that all of the rows in our original matrix are needed if we wanted to find a basis for that row space. We don't throw any of them out. So that would imply that the rows of A are both linearly independent and that they span all of Rn. That's what it means to be a basis. That's two more of these statements here. The row vectors of A are distinct and linearly independent, and the row vectors of A span Rn. But again, remember, the rank also gives us the dimension of the column space. So the same conclusion can be made for our column space. The column vectors of A form a basis for Rn, so that means they span Rn, and they're linearly independent. So that right away gives us it gives us n and o, h through k, and in fact it also gives us l and m, because that's saying that the column vectors and the row vectors both form bases for Rn. All that's left to show is these last two statements, but again, we kind of already did this as well. So it says the orthogonal complement of the null space is Rn, the orthogonal complement of the row space A is 0. So again, if we're saying that the row vectors of A form a basis for Rn, then that means that the row space of A is Rn. That's what that means. So if we're looking for the orthogonal complement, let's go down here, the orthogonal complement of the row space. Well, that means that we're looking for the set of all vectors that's orthogonal to all of the vectors in Rn. But using this theorem that we talked about over here, without proving, the only vector common to W and the orthogonal complement of W is 0. So that means that clearly the 0 vector should belong to this, but nothing else from Rn can belong to this. Otherwise, these two subspaces would intersect at more than just 0. There's nothing else in there's nothing else available if we're not allowing any other vector in Rn to live in this space. So that establishes this one. And the null space of A, remember we said that the null space and the row space are orthogonal complements. So again, the orthogonal complement of the 0 subspace should just be Rn. Again, that was a very informal sort of talking through of these equivalences, but I encourage you to look at the book to see the more formal treatment of those. There's a little bit left in section 4.9 that we're not going to cover. It's optional content. It talks about overdetermined and underdetermined systems. It's important stuff, but we're not gonna we're gonna skip that. There's also a little blurb at the end of 4.9 before the optional content that talks about some applications of rank, which is worth mentioning because anybody going into computer science, this is something that they're going to see again. So just if you're interested, you can look at that. It has to do with, or the discussion in the book has to do with compression algorithms for transmission of data across a network like the internet or something like that. Basically, the idea there is that if you have data that's stored in the form of a matrix, and if that matrix has a small rank, remember. A small rank means that the row space of the matrix has relatively small dimension, and if you have several rows in your matrix but the dimension is relatively small, that means a lot of the vectors that are showing up as row vectors in that matrix are redundant in the sense that that set is linearly dependent. So kind of like the plus minus theorem, we can throw out all of those quote-unquote redundant vectors to reduce that down to a basis for our row space. And so in a sense, rank is a measure of redundancy in the rows of a matrix. So what we do in some compression algorithms is we take data that would be normally stored in a matrix with a high rank, and approximate that with a lower rank matrix, basically throwing out some of the unnecessary or redundant row vectors in that matrix. And that's done in a very specific way. We're not going to talk about how that's done here. That's better left for a different class, but I just bring that up just in case anybody's going into computer science, and that's one application where you're going to see the discussion of rank. But we're going to go ahead and leave that there, and that's going to wrap up chapter 4 for us.